Cohort. Who's the nice gentleman? Are you busy? What are you doing? You're sending a message to your friend, no? Would you mind switching the, yeah, please, the power, yeah. Just once, yeah. Thank you very much. Ça va, c'est well done. Pa, 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 pa. So today we're going to be talking about something else that we're going to get into ways of ensuring either the confidentiality or ensuring a digital signature. We talk about digital signature today, but before that we need to talk about MAC and hash functions. Let me get this on shared upward. One moment. Hey, is anybody on Moodle, on Zoom? Is anybody logged into Zoom? Does anybody want to log to Zoom, onto Zoom? Just to make sure it's appearing. I don't mind. I'm not asking you to log. You don't have to log in, but just to make sure that.
What's the key for it?
Yeah. So yeah, it is. Yeah. Okay. Thank you. Just follow it up. If it doesn't display what should be displayed, remind me, please. Right, so just before we start, I just want to revise. I tend to not remember what's meant by confidentiality. What's a confidential document? And have a go. It doesn't matter if you're wrong now. It's in the exam, is that what matters, right? That's why I'm asking now.
That to make sure just one person they can open the message.
Okay. Instead of the wrong, let's say
authorized person can.
Who? Authorized. So let's say all the authorized person can not open, sometimes open, but they cannot. They can still open it but can't read it. So
they can read
it be disclosed. We say disclosed. Because sometimes you can't say read because sometimes it's not something to be read. Maybe a picture you just watch. So disclosed, it means read or watch or video or whatever it is. So,
access. Like only authorized users can access it.
No, access is different. You can access a file, but maybe you can't open it, or maybe you can't delete it, or maybe you can't read it. So no, you have to be careful in the word you use. It may not mean confidentiality. Right, what about integrity? Integrity of a message. Integrity of a message? Yeah. Okay, except if the change is authorized. So again, be careful. If it's an authorized change, it's okay. If there is unauthorized change, the idea, okay, it doesn't change between this while you're sending it, just to get you the idea what integrity is. But you have to be a little careful. some authorized changes are okay, and still the document maintains its integrity. If somebody makes a change that they're not supposed to make it, or it shouldn't have been made, well, then the integrity is lost. Close the door properly. Right. What's the other? So it's confidentiality, integrity. What about the authentication, an authentic document? Yeah, I should be actually, no, don't answer that. What's an authentic document? I just want to switch to the other side. Authentic document? Authentic document?
It's to make sure that the sender is.
Yep. The message was sent by the sender, the correct, or the sender whose name is there on it. And if you're talking to somebody, you want to authenticate that person, then to make sure that you're talking to that person, and they are as they claim to be, or who they claim they are. Okay. So now, talking about integrity. So now we're going to concentrate on integrity and authentication. Integrity, making sure that the message is not changed. All encryption systems, they provide this capability of integrity. Like if you encrypt a message and send it to somebody else, they decrypt it. If it has been changed along the way, it will not decrypt correctly. It will not show the message. So all encryption systems are successful at 100% providing the integrity of a message. But what's wrong with that? What's wrong with using encryption systems to provide integrity? The problem with encryption is they're too slow, especially if the message does not have to be confidential. I might send you a message. It's not confidential. I don't mind if anybody reads it, but maybe you need to know it came from me, or maybe you don't even need that. Just as long as you get the message without any change. So integrity, but we don't want confidentiality. So in that case, encryption is very slow. And that's the reason why they came up with two new or different systems. They're called special codes or techniques for authenticating or making sure that the message is authenticated or it has integrity. Integrity. They all can be used, but we know it's a little slow. The message authentication code, this is a technique, we'll talk about it now. So these are the three techniques that can be used. We've talked a lot about encryption. Now somebody else is arriving. Close that door behind you, please. I think we'll have one of those. It should have been there. I'll report it. So the next few weeks we'll have it closed on automatic. Been done a long time ago. Okay, Kamush. Tamam. I have to get the word be quiet in 6 languages or 8 languages. Okay, so now we're going to talk about, we'll start with message authentication code. It's a very simple technique. This is like hashing. Authentication are quite similar techniques, very little difference between them. And they are one-way function. One-way function. What's a one-way function? Anybody can give me general description. It don't have to be right or accurate. What's a one-way function?
It is just, if we encrypt it, we can decrypt it.
You can't decrypt it, yeah. One-way function is any calculation that you can do in one way. It's easy. You can do it in the opposite direction. Some people say it's like taking your toothpaste out of your toothpaste tube. You squeeze it out, but if you squeeze it all out, you can't kind of easily put it back. That's a one-way function. That's from a practical thing. But mixing liquids, if you take two liquids and mix them, it's going to be very difficult to separate them. Maybe there are ways to separate them, but they're not as easily as mixing them. So this is what one-way functions are. And we use one-way functions in a pretty much to provide the integrity of a message. So how do we do it? And what's the major advantage, the major point for those two techniques, marking or hashing? They are extremely fast, much faster than encryption, even though they do some sort of encryption. But they shrink the message. They always, well, but maybe shrink is not the right word. If the message is big, they reduce it to maybe 500 bytes. If it's small, they'll also produce 500 bytes. They always produce a fixed output, small output. That's a good thing about them. The output is small and they can authenticate the message. How do they authenticate it? So that's what we'll look at in the next half an hour. And then these are the foundations as well. Together, those for digital signatures. For digital signature, we use either message authenticating and encryption or hashing and encryption. And that will give us the digital signature. So first we look at macking and hashing. How do they work, or what do they consist of? So message encryption by itself also provides a good measure of authentication, of integrity, and of confidentiality. But sometimes we may not want that. We may not want the confidentiality part. If you want confidentiality, you have to use encryption. These other two functions, that macking and hashing, do not provide confidentiality. So if a public key encryption is used, we can provide, encryption provides no confidence of sender. What do you mean, no confidence? Since anyone potentially knows the public key. Yeah, if we want to send a message that's confidential, then I can use your public key and I send you a message and sign it Faheem. But anybody else could have done that, cut your public key and wrote a message and signed it Faheem and sent it to you. Signed it as in just put their name down. However, if a sender signs a message using their private key, but if I send you a message using my private key, then you can authenticate me beyond doubt. Again, we should be able to identify a message as corrupted. So if I send you a message and somebody changed a couple of bits in it, we should be able to identify them. Encryption will identify them, but at a cost of two public keys use. But if we need to have confidentiality and also authentication, then we need to encrypt the message twice, right? So we use something called message authentication code. And message authentication code is generated by an algorithm that creates a small and fixed size block. So it takes a file or a message, whether it's small or a big file, it'll always produce the same size block. Depending, obviously, what's in that, some sort of encryption that goes into. So it's different from one message to another. But the good thing is that they're always the same size and they're fixed size. That's what you produce. And also, it's much faster than encryption, a lot faster. So, and what we usually do, we take the message and append the material onto it. So if you have a message you want to encrypt, or a file you wanna mac, here's the file. You just perform the mac operation onto it, and it generates a small code at the end. Sometimes they call it a digest. They have different names for it. Sometimes they just call it the mac or the hash if it was a hash function. But whether the message you want to send is small, you still get the same digest, the same size digest. But this digest that you get here is different to this digest that's here. So each one is linked to the document it digests. It's like me giving you a book and say, can you summarize this book for me in one page? So we might look at it and say, oh, this is a book about security. So you're right, this is a nice book about security discussion. And then I give you another book about programming. I say digest it. So that one single page is always going to be different for different books or for different messages. So this digest that we are looking at here is different. And if you run the same algorithm, you produce another one, another digest that's similar. So what we do, this is your message. This is clear, plain text message. Everybody can read it. And we summarize it. For now, I say summarize it. But we perform the algorithm. Now we produce this kind of unlegible code. It makes no sense, but it's strongly linked and associated with that message. Now we take all those two and send them. So you send the message and you send also the digest with it. And the receiver receives the message as well. Now, if the receiver, the message is not encrypted in any way, and it's not confidential, but if the receiver, this message, a digest, it should be the same as the digest you send them. So you send the message and you send a digest with it. But the receiver will create a new digest and check, are they the same? Are they equal, those two digests? If they are equal, then this message was not modified. Just for argument's sake, let's imagine the message you're sending is 5, 2, and 3, for example. And just imagine the digest is summing up the number. So this guy here will send, for example, number 10. This is just an example so you get the idea. So I not speak over your voices, guys, so please stop talking. Well, that's the message I'm sending, and that's now the digest I'm creating for it. When I send it over, let's say the message was received exactly without any changes. So the receiver also performs the same the same algorithm. But now, this is not how the Mac works. But let's say he just adds them up, and he says, okay, they are now 5 plus 2 plus 3 is 10. And they've received so that's the digest they received from us. We send the message and the digest. But the receiver also creates its own digest, and if they are the same, then it'll say, oh, this message was never changed. Because if, for example, during transmission of this message 532, let's say this 2 turned into 1, just for argument's sake, then when the receiver receives it, it'll say, oh, it's 5 plus 1 is 6 plus 3 is 9. That's the digest the receiver creates, but that's the digest that it received from the sender, that the sender created. And if they are not the same, then they say, oh, hold on, the message has been modified or something happened to the message. So that's the basic, simple idea. The sender sends the message in clear, plain text and performs, before sending it, of course, it performs an operation on it called the MAC operation, which is a simple encryption, very simple encryption system, but in a way that you cannot bring it back. But it's already, we call it the summary of that message, or the digest of that message. There are many different names for it, but it means it's a summary of that message. But it's very strongly associated with that message. Like that number 10 is really strongly associated with that message. We have another file with another list of numbers. It will not have, say, for example, the number 10. We'll have a different number to be associated with that message. But anyway, in simple terms, the sender takes the message, map it, that means perform the MAC operation on it, generate this digest, sends the message on the digest to the receiver. The message is not encrypted, it's not confidential. The receiver also performs the MAC algorithm on the same message, will generate its own digest. Now it will compare the digest that it received from the sender with the digest the receiver created. And if they are the same, then it will assume, most likely, 99.999% the message was not changed. There's still slight possibility, but this is how macking works. So it's basically appends to a message some signature. The receiver performs the same computation on the message and checks it matches the same MAC. It provides assurance that the message is unaltered, and that's integrity. So it provides integrity of a message. So here's in the diagram is the actual, is there annotation? Right, so here's the, for example, the MAC algorithm. It takes the message in and the MAC, it requires a key. And the sender and the receiver share that key, even though that key is not changed often, it's not, but still, two users might decide agree on a separate key, on a different key. So it using that key on that message, it will produce that MAC. So now the sender sends the message and the MAC created. The receiver receives the message and the MAC. It performs the same operation on the message and creates its own MAC. So this MAC here is created by the receiver running the same MAC function using the same key, and it produces its own MAC output. And it should be the same MAC that was received from the sender. So when the receiver receives this message and the MAC, it kind of separates them. Usually they're appended to one another. So it takes the message separately and produces its own MAC, and then takes this MAC and compare it with the MAC it created. If the two MACs are identical or equal, then the message is assumed to have no changes. So this assumes both some of the properties or differences between this and hashing, as we'll talk about hashing in a minute, that both users here, they share a key. The procedure, the sender computes the MAC of a particular message. It's kind of using a particular key, and it produces the MAC. So, and then it sends the actual message and appends the MAC to that message, and the receiver will separate them and generate its own MAC, and the two MACs are compared. MAC is similar to encryption, but does not need to be reversible. So it's much simpler, easier, and faster. So this is the actual proper diagram. Now, if we are to use macking in digital signature, we need to add an extra 1 bit to it. Now, if you want to sign a document, if you want to sign a message, if digital signature is authentication. So if a sender sends you a message, you want to know if this message came from that user. It doesn't have to be confidential. The best way, well, the way we've learned how to send an authenticated message is to take a message, I want to send it to you, I'll encrypt it using my private key and send it to you. If you receive that encryption, you can decrypt it using my public key. If you manage to, if my public key will decrypt it, well then the message was encrypted using my private key. And that's the way we use for authenticating. If you want to know, did the message come from me, then just use my public key to decrypt it. And if it works, that means for certain I sent you the message. That's authentication. And that's fine. That's really the basic idea of digital signatures as well. Except for digital signature, it will be handy enough or efficient to send small messages, and I'll encrypt them with my private key. But if the message is a big file, then it's going to be very slow to authenticate a message. That's the reason. And so from that point onward, they say, from now on, when we want to do digital signature, let's shrink that document, let's produce a summary of that document, and then encrypt the summary. Don't encrypt the whole document. And that will make digital signature much, much faster. So that's the basic idea of digital signature. Instead of encrypting a file with your private key as a sender, no. Well, get a summary of that file and only encrypt the summary and send it, and the receiver decrypts the summary, the encrypted summary. So this is how digital signatures work. We need this MAC-in operation. And the reason for the MAC-in operation, because it's faster and gives us still a mini file of that big file, still related to that file. That signature, that summary that we have is strongly related to that file. It's not going to be similar to any other summary for any other file, but most likely not. But there's a minute possibility. And then we work on that digest. So this is the way it works. This is how digital signature work using MAC. So we take the message. We're going to send it, bring it really without any encryption. But we will summarize it. We run the MAC on it. The MAC is very fast. So, and it will reduce that file and produce a small summary of that file. 500 bytes. It's always 500 bytes. Doesn't matter how many millions or billions of bytes the file is, you're always going to have 500 bytes or thereabouts. So it's fixed size. So once we produce that, then that's the part that we will encrypt using the private key. RS, that means the private sender key. Reading it backwards, so the sender's private key. Normally, how we authenticate anything that you want to send. But instead of encrypting the actual message or the file, you summarize the file using the MAC technique or the MAC. Use it to a very small size, and we encrypt it using the private key, and we append it to the message. So the message goes in plain text, it's not confidential. And we put that signature. This is called now the digital signature. So your signature is actually an encryption of the summary of the message. So any file you want to send, summarize it, get the summary, encrypt the summary. That's going to be the signature for this file, because the summary is associated with this file. And when you encrypt the summary, then that's the digital signature that's associated with that message. And every message is going to have slightly different signature. When you sign by hand, your signature is always the same. You try to make it exactly the same. Now in digital signature, every time you make a digital signature of a document, it's going to be different, and it's related to that document. But it's always going to be encrypted with the sender's private key, and it has to be decrypted. What do we decrypt it with? The receiver's key or the sender's key? How do you decrypt a message? If I send you a message encrypted with my private key, how would you decrypt it? With my public key, yeah, of course. Okay, so now we got to this point. We have the message, we have the encrypted summary of the message, or the encrypted MAC. They call this the MAC. So we encrypt the MAC and append it to the message. So here's the message, and here's my signature at the end. Now, when the receiver receives the message and the signature, separate them. They are appended, just simply appended together, split them apart, and we decrypt the encrypted signature. Of course, we use the sender's public key. Look at this idiot who wrote that. See? This guy says the receiver's public key. Yeah. I don't know, whoever, it wasn't me. Actually it was, but okay. So that should be, this is the sender's private key, and this should be the sender's public key. Right. Okay. Now I know, I was just testing it to see if you discovered. Right, so that's done. So now we have, so remember, this digest was encrypted. Now we decrypt it to get the original digest. And in the meantime, we take the message and we MAC it as well. So the sender generates a MAC, the receiver also generates a MAC. And so that's the receiver's MAC, this is the sender's MAC. We test them and we see if they are the same. If they're the same, then there's no error. And if they're not and if they are the same, then we know the message was not changed, but we also know who sent it. And this is what's called the digital signature. So the digital signature is an encryption by using the sender's private key and decrypting it using the sender's public key of a summary of a message. So all messages are first marked to reduce their size, but if the message is only one line, or so it might increase size, but that's okay, that's not too slow. So message authentication, as shown, MAC provides confidentiality. Does it provide? Does not provide confidentiality. What? Probably done it when I was out of my mind, right? Or does anybody, is there something wrong here? Is there something wrong in the first line? It says, as shown, the MAC provides confidentiality. MAC does not provide confidentiality. Just to this, I put this on purpose. So just to hammer the point that MACing does not provide confidentiality. What does it provide? Integrity. It provides integrity, and if it's used with encryption, with public key encryption, it can also provide what else?
Authentication.
It becomes a digital signature that provides authentication or identification, right? So generally used, it can also use encryption for secrecy if we want to. If you want, you can encrypt the message, but the main purpose of digital signature is to make sure two things: the message was not changed, and you know who sent it for certain. Generally, use separate keys and can compute or after encryption is generally regarded as better than before. Okay. Why should we use MAC and not use encryption systems? Because it's a lot faster this way. When you MAC a message, you reduce its size. If you need to encrypt it, it'll be much faster than encrypting the original file. And also, sometimes you only want authentication, you don't want confidentiality. Remember, encryption provides confidentiality if you want it to. And if we need both here, you have to encrypt it twice. And sometimes we need authentication to persist longer than the encryption. And note that MAC is not a digital signature. The MAC alone is not a digital signature. Only if you encrypt it with the actual, as shown, the MAC does not. Provide confidentiality. Okay, let's go to the next one. Properties of MAC. MACing. This function that's called MAC. What can you tell us about it? Its properties. First, remember that it needs a key. The sender and receiver need a key. It's like encryption, like conventional encryption. Both sender and the receiver, they need to agree on a key. It condenses a variable length message. So it takes any message of any size, but it will always produce the same output, fixed size output. And it uses a secret key and produces a fixed size authenticator. We call that the authenticator. That's the encrypted summary. And it's many-to-one function. What's many-to-one? It means, for example, you produce this list, and maybe it doesn't work by summing up the numbers, but let's say we sum them up, and those numbers are 10. Obviously, if you have another list, 173, it's not going to be 10, it's going to be 10. But sometimes you get another different list. For For example, 5-1, and you add summarize it and it gives you 10. So here there are two different messages and they give us the same digest. So sometimes it's possible. That's what they mean by many to one. So where is the many to one bit? It's a many to one function. That means it's possible that few files will actually produce the same digest. It's possible. But the point is, it's very difficult to change a message and get the function to produce the same MAC. So it can happen that you accidentally take another message, completely different message, and they might produce the same MAC. But if an attacker, for example, somebody wants to change this message, but it's so simple here, right? But if I want to change this message, I just, for example, this is I'm gonna get paid 5, but I'm gonna maximize it to 9. But I want to do it in such a way that the whole, again, still give me 10. It's gonna be very difficult to work that out. Same change, because the actual function is a bit complicated that it cannot be broken so easily. But just remember that if somebody has time, they can actually produce a message with a similar digest different to that one. But most likely that's not the change you want to make, but still it's possible. So it's many to one, meaning there are multiple messages that might produce the same MAC. But potentially many messages have the same MAC, but finding these need to be very difficult. It should not be easy to produce it. Otherwise, it loses its power, its function. So the requirement for a MAC, you must take into account the types of attacks. You need a MAC that satisfies the following. Knowing the message and the MAC is infeasible to find another message. So this is an important condition. If you knew this message and this MAC, it's going to be very difficult. Now I was able to produce another message that gives me the same, but then this adding thing is not a good MAC function. The MAC function has to be strong enough that it's going to be very difficult to find, you try and find out another message that will give you the same MAC. So that's a requirement. So if you come up with a new MAC message and you say, guys, here's my suggestion for a new MAC message to be used. That's the first test they do to it. How easy is it? Okay, take a message and MAC it and show me the summary. I'll take the message and I'll take the summary. And I'll try and find another message that gives me exactly the same summary. If I find it easily, then your MAC function is not good. So that's the first requirement. Second one is MACs should be uniformly distributed. So the MAC should be uniformly, this summary that you produce should be uniformly distributed to the entire document. Doesn't matter how big the document is. So if you change a character or a number or somewhere in the file, somewhere, it should reflect on this. So it's uniformly distributed. And MAC should depend equally on all bits of the message. That's, like encryption. If we talked about encryption functions before, that it's one of those properties that it's the completeness. That means that what you produce here depends on every number message. So if you change one bit in the message, you should have a change here as well. It's like encryption. So this is what we should have seen first before doing the digital signature. This is the MACing. So if you're asked to describe MACing or explain it, you get a question to explain MAC, what is MAC, and explain how it works. MAC stands for Message Authentication Code. It's a function that's used to provide integrity of a message. How does it work? We take the message, we MAC it through the MAC function. There's a key used, don't forget the key, it's important here, and it generates a summary, or they call it, the summary or the MAC of the message. Append it to the message and send it. It's like you give me a message, a book, I summarize it and send both of them. So what the receiver does, separates the message from the MAC, keep the MAC separate. That's the MAC that we receive from the sender, generated by the sender. We run the same function using the same key on the same message, hopefully, and it should produce the same MAC. If these two MACs, the MAC that's generated by the receiver and the MAC generated by the sender, if they are the same, then we assume the message was not interfered with. The integrity was maintained. If the message was changed here, then this MAC would be different to that. Well, that's the MACing system. How do we use this into digital signature? It's the same, but after you finish the MACing, put here the encryption by the sender's private key. So you encrypt this, and then it has to be decrypted using the sender's public key. Using symmetric ciphers for MACs, it can use only block cipher, change mode, and use the final block as a MAC. So in some systems they use the actual encryption, simpler encryption ones, and they take it block by a block. For example, they start with a message at the beginning of the message. For example, this is the message, so they start like this. Go to the first block, they operate on it, and then they include the operation of this, and then this and this. So it's cyclic operation that involves each and every block. You take the result, maybe, for example, you add a number, but just if we take the add, I find adding is the simplest thing to do. So for example, this is just numbers. You start with a number and you add it to this one, that's whatever, let's say 5, the key is 5, you add it to 7 becomes 12, you add 12 to this number, keep adding to this one, and there's a macking or modding, and then you end up with a number, that number becomes your summary. It's similar in a way to the block cipher, and the last block becomes your final kind of digest. It can be used that way. Data authentication algorithm is widely used MAC-based DES system, but it's no longer in use. So let's use this now as authentication or as digital signature. It's the only use we'll consider. We won't be considering authentication, but authentication is again just encrypting the digest. So to authenticate a document, MAC that document. Well, I didn't run the attendance bit, so. Just in time for hashing, guys. Okay, so let's talk about hashing. Well, hashing is quite similar to MACing, same idea. Hash function is another function that's one-way function that you cannot reverse it, you cannot work it out, but it's also fast function. And the good thing about hashing, the only difference between hashing and MACing is that hashing does not need a key, does not use a key. MACing must use a key. So that's one of the major differences if you ask what's the difference between MACing and hashing. With MAC, in order to MAC a message, you need the key. The user, the receiver and sender, they require a key. But with hashing, there is no key involved. Any message, if you perform the hash function onto it, it will produce a small hash. They call it hash. That's the summary of the message. And if you are to talk about it, it condenses a variable length message into a fixed size, smallish hash. Some books or some applications, they call it fingerprint. This is like a fingerprint of a message, of a book. They say you take a book and you produce a summary of that book. It's like a fingerprint of that book. Some call it fingerprint, some call it digest, and some refer to it as a hash. So any of those terminologies, are okay, and it's used in many documents and many books. And it's assumed to be public. The hash itself is assumed to be public. And some hash functions are better than others at operation. I remember the many-to-one I mentioned here about the Mac. Also hash functions, they suffer from that problem as well. It's a many-to-one function as well. What does that mean? Usually it means if you want to hash this message, you perform the operation on it, you get this hash. They call this the hash. The hash of the message. Now, sometimes you get another message that might give you the same hash. It's not common, but it's possible. But still, if you have a hash function, that will be easy to produce another message, modify the message in such a way that we can produce the same hash, the same summary of that message, then that's a weak message. And they call these collisions. I don't know if you've come across hash functions in other computer science topics. If you did, hash functions is one way of organizing records on files. Did you come across that? Do you know how? Guys, I'm going to ask you to leave if you keep on talking, please. Talk to us, ask us questions, or share the story with us. In databases, you have a file of records. The operating system, or how does the database know where the record is if you ask for a particular record? For example, you have students' records, right? A database or file of students. There's student number, student name, whatever, nationality, all the details of a student. How does it actually reach a particular point? And what's the quickest way to find a record in a student file? Have you programmed? Have you done any programming? Index, yeah. Indexing is one technique. And what's an index? An index is just this field. You find a key field in the file, like unique field. Data that's unique in that file, that's like student number or staff number or whatever it is, and record number 0, 1, 2, 3, and all that, the order. So that's all you have. That's what an index is. So an index is kind of a small version of the same file, but only the key field. And now you order this. The other difference is that you order this based on that key field, the student number. For example, this student number 500 here, and number 200 here, and number 700 here. This is not sorted. But if you have it sorted, if you have student number 200, and then 500, and then 700, this is a sorted file. Searching sorted files, there's so many algorithms for searching through a sorted list. Say a binary sort, you can maybe, a list that has 1,000 records, you can maybe 4 or 8 comparisons, and you find that record. Like there are so many quicker ways to, so this is the point. If you're looking for a record, let's say you're looking for a student number, I don't know, 628. This is the student record, you want that record. And here, student record is in record number 420. So you search for it quicker here, and you'll find the record when you go straight to it. That's the idea. So in the main file, especially if the file has 1 million records or so, if you want to go sequentially search for it. So anyway, the point is indexing is one way, one technique to access files. Any other technique anybody knows of or heard of any other technique that's used to access records in files quick? Yeah?
Hash tables.
Hashing. Yeah, hash tables. Is it hash tables? I don't know if they're hash tables. Maybe they are, but it's called hashing. All you need is a hash function. The good thing about hash functions, it doesn't need any record. See, the hash function is a function, you give it any student number, for example here, student number, whatever it is here, 642, and it'll tell you it's in record 400. It's a function that once it runs, it gives you the location immediately. So it doesn't even need to keep an index. A hash function is between 0 and whatever, the maximum student number we have. It will give you a number, but the maximum number of records. Well, how does it know? How does it? Well, initially you start with an empty file, and the hash function, okay, now we're going to enter student number 642. Give me a location. You put this in the function to give you a number, 400. You put that in record 400, so you fill in here. So the hash function can tell you exactly where it is. The quickest way to access records in a file is hashing. That's the fastest possible technique. It's faster than indexing, because indexing, you still have to go to the index and search it. Okay, it's going to be binary search or whatever the fast, quick searches, but still, you have to search it. Plus, on top of that, as well as the file, you also need an index, like another space on the hard disk. So while hash function doesn't need nothing, it doesn't need any extra information or space on the hard disk, that function is a software. You run it in your program. Call this hash function, give it this number, give you a number. You go there, you find your record. You either put your record there or you pick your record there. Anybody knows any disadvantage of this hash function? Why don't we always just use hash functions? They're the fastest, quickest way of accessing records. Pardon?
It might be cloning.
Maybe what? There's collision, yeah, if that's what you said. So they suffer from something called collision. Anybody knows what collision is in hash functions? Yeah, I know you know, thank you, I just wanted to know. So, for example, if this record 642 gives you this location, it says we have student number 642, and the hash function saying put it in record 400, in place 400, position 400. You might, maybe other records will be put in different locations, but sometimes you give it another number, student number 1105, it will tell you put it in number 400. That's a collision, where it gives you the same location to put two records. That's a problem with hash functions. And the better hash function is the hash function that gives you no or less collisions. Okay, I just thought I'd mention this, but this will probably make a lot more sense to you. But that's how hashing is used in files and in accessing records in files. So if you haven't used it, look it up if you're into programming. Sometimes they're handy in some applications. They're extremely fast and they use very little resources, no space on the hard disk. But they have disadvantages. They also, with indexing, you can have an index on, say, on nationality, or index on serial number, or index on specialization, or whatever. You can have multiple index for the same file, but with hashing, you can't. You can only have one hash value on one of the fields. And with hashing, anyway, so you can't read it sequentially. But let's go back to our functions. So there are different, developments of hash functions, algorithms, but they do the same thing as the Mac. A hash takes a message of any size, a file of any, it doesn't matter whether it's a small message, big size, or big message. It will go through the hash function and it'll produce a fixed amount or fixed size output. That's the property of hash functions and Mac functions as well. They take variable record size or message size or file size, you pass through them. They are normally a cyclic operation like CRC or, I don't know if you, and so it keeps working through it until it finishes through all the blocks of the message, and then at the end it comes out with the same size output. And it's different from one message to another. So that's the general idea. Hash functions condense an arbitrary message of any size into a fixed size. Usually assumes that the hash function is public and it doesn't use keys. That's another advantage of hash functions, they don't use keys. Hash is used to detect changes to messages. So what's the main purpose now we're using hash here is to provide integrity. Just as long as your message is not changed. So when we do exactly the same thing we've done earlier on with macking. It can be used in various ways with the message, and most often to create a digital signature. So hashing can be used just on their own to provide integrity, or with the public key encryption system to provide digital signature. And this is the most used technique for digital signature. And that's used for authenticating, users. So how does it work? There's a hashing algorithm. You pass a message through to produce hashed text, or not necessarily text, it's just hashed, the hash. It's what hash functions are used for. They're used for direct access to files. That's the one I was just talking about. But that's not of our concern. We won't be asked about files, accessing files here. Here we are more interested into the integrity and the digital signature. And so it provides message integrity. It provides a one-way use for storing passwords. So in fact, passwords, again, there's another use for passwords. Almost all new applications, they never ever store the passwords. If you write an application hopefully for your dissertation, whatever your application is, but for example, you log in, and you log in and you ask for the ID and the password, and the user types the ID and password, and then you have them somewhere in a file. You go and search for a record of all the users. You find the user ID and the user password. And if you have the password here in clear text, it's not a good idea. Because if somebody accesses that file, you can have access to all the passwords that everybody in the organization. So they never use passwords, they never store, and don't do it. If you are doing a dissertation project here, next semester or the following semester, and you write an application, make sure, because that's the first thing the examiners, they go and say, okay, can we see that file? Show us the passwords, and you show them, happily, you're happy, you can access and know when there. Here's the file. This is the password I just entered, and they can see it. Then that's a bad thing. That's bad news for you. That's 10 marks gone, or 5%. You just lost them. So we don't put plain text passwords. Nobody stores passwords anymore as they are. What they do, we take the password and we hash it. So we pass it through a hash. It gives us something else, illegible. And if you take it, you can't go and feed it as a password. So all passwords, you don't ever store passwords anymore. Store the hash of a password, and you can leave it, don't leave it available, but even if somebody gets access to it, they will not be able to work out what the passwords are, because hash functions, remember, if you put down, for example, the password is Ireland or Irish or something like that, and then it gives you MST2OB, right? Why can't you then bring it back? If you have the hash, can you work out what the original password is? No, because hash functions are one-way function. They encrypt, there's no decryption algorithm for them. Right, so, and there are also hash functions are used in digital signatures. So hash functions are huge, fantastic. They're used a lot. They're great use, they're extremely fast and reasonably powerful, yeah?
Well, I think if your server is compromised, whether your password is hashed or not, it's of no use.
Yeah,
because I can easily I can create a user, copy my hash,
yeah.
replace it with another hash, and I can log in as that.
No, no, you can't. Well, not that way anyway. It doesn't matter. The hash will always give you a different hash. If you take that one, you put it through the hash, it's not gonna give you the original password, give you another different hash. They are one way. But if you have a way, nice. If you have a research or something like that, You can continue with it. You can turn all these hash functions are useless as, because that's what we use them here for keeping the integrity of a message. Like if I send you a message and I hash it, I mean, that's clear for you that this message has not been modified, as we saw earlier on. But if somebody else can produce another hash function and mess it about, I guess with time it can be done. We're given a lot of time and processing. But that's another reason why during transmission, usually they always include the time and date. So if you receive a message that's been sent 10 minutes ago, you can almost be certain somebody held it and played with it and then retransmitted it. It doesn't take 10 millionth of a second to go around Earth. So, but even if you have a program that can actually attack a hash function and produce another message similar, that can be sorted, and sent instead of that will generate the same hash. It's going to take a long time to do. So anyway, let's get back to hashing. Let's just get the idea. So the idea is simple. You have a message, you hash it, you get the hash. That's the summary of that message. You send the message and you append the hash to it. The receiver gets those two. Separate them, split them. That's the hash that was created by the sender. The receiver also puts it through a similar hash function and gets another summary. Compare those two summaries, and if they're the same, they assume no change has happened. So the message integrity is maintained. It's very simple. You need to be able to explain it, but that's not much of a, it's not difficult. The other thing now, if you want to turn this into a digital signature, we need to use the sender has to encrypt the message, or encrypt using the sender's private key. But instead of encrypting the message, which can take a long time, we encrypt the summary of the message, the hash of the message. So to turn this into digital signature diagram, all you have to do here is add the encryption algorithm using the sender private key, and here you use the decryption algorithm using the sender's public key. An example of input and output to a hash function. They have the same, maybe the same size input. They'll always produce a fixed size output. The fixed size is always the same one, depending, it doesn't matter how big or small the input is. But as you can see, with one bit change, you get completely different hash function. So it depends on the whole message, and one little change will give a big change. What's that property? If you have a small input change, it will generate a large output change. And this one just shows that different size messages will still produce the same output hash size, regardless of the size of the input. Because it just works in one block. Doesn't matter how big a message is, it takes it one block at a time and operates on it, and it always ends up with the same size message. So if you have a message and you hash it and encrypt it, that becomes our cryptographic hash function. Cryptographic, I don't know what's the idea here. Larger messages. So the famous hash functions, they have hash function A1, SHA, secure hash algorithm. This is a standard. So the hash function, the steps for it are well known, the algorithm is known, and it generates a block of 512 bit blocks, produces hash of 160 bits. So it takes the message, breaks it into 512 bits, and this hash function, sh1, will generate a hash of 160 bits. It starts with hash called internal or initial state, and then starts operating on each hash with each block, and keeps generating different hashes as with the blocks until at the very end, when you have the same, the final value is sent as a hash. So the message is actually broken into multiple blocks. You start with an initial value and perform the function that's on this block, and then the output is performed on each block. So the block is taken as an input, and whatever the message from the previous, or the hash from the previous block is taken, and the same hash function operates. And at the end, you end up with whatever the last block you have is your final hash, depending on how big how long the hash function is, or how long the message is. The message transformation to bit sequence creates a number of blocks. Okay, it explains the same thing basically. So just want to go, and when it's finished, you send the message, your original message, and append the actual hash onto it. Another diagram of, it's a recycling or cyclic kind of operation. You take one block at a time, produce it, and bring it up again, and recycle each block until you finish all the blocks. And it can go up into round, it takes as many rounds as the message, how big the message is, depending on the size of the message based on the blocks. The properties of a hash message, not conditions, but yeah, and characteristics of a hash function. Again, let's start with this one. It should be computed on the entire message. This is the completeness, the property of completeness. There's no part of the message that doesn't enter into the calculation or into the function. And it should be applied to any size message. Say, come up with a new hash function, you say, oh, it won't work on messages that are bigger than 10 kilobytes or 100 kilobytes. So it will work on any size, small or large, and it should produce, the required protection. And it should produce a fixed length output all the time. A hash function always, doesn't matter how big or small the input is, the output is always fixed. Now it should destroy the homomorphic structures in the underlying public key crypto systems. That means be unable to compute the hash value of two messages combined given the individual hash value. So the idea is the same. This is where we said earlier on, hash functions are also many to one. That means, what does that mean? Here's a message one, sometimes message number two, they give exactly the same hash. So it's possible, but it could happen accidentally, but it's very difficult for somebody to say, right, here's the message and here's the hash. Can you generate, give me another message that has the same hash? It's almost not impossible, but it's extremely difficult. That can take a very long time. And if you just have the hash, they say, give me two messages that produce the same hash. This is what this means. You cannot do that, or it should not be possible or easily or to do it. What else can you say about a hash function? What are the other properties? If you need to talk about it or ask about properties, it should be easy to compute a H for any message hash. So it should be so simple and fast to go in one way to produce the hash, but it's very difficult or takes a long time or almost impossible to produce the message from the hash. You can't actually, because this hash can produce can be produced by multiple messages, but which one it is, it's gonna be so difficult to do. It should be one-way function, so that messages are not disclosed by their signature. Okay, so it's like encryption. If I give you the signature only, the summary only, the hash of a message, you can never really work out what the message is. But it's no good to anybody, I guess, except with the password. Remember when we said you store the password, you take the password, you hash it, and you store the hash. So anybody now that want to give you the same password, you have to hash it and compare it to the hash that's available. But they cannot work out what the password is. If you have a technique, I'd be interested to hear of the, or you can take it on to your research at the project. But I doubt if there is an easy way of doing it, a successful way. But okay, and it should be computationally infeasible. That's a condition for hashing function. Like if we find a hash function that can be computed, then it's not a hash function. It wouldn't be used anyway. But it should be computationally infeasible. That's not impossible, but infeasible. Given a message and its hash value to compute another message with the same hash value. It's possible, but you need a bit of time. It won't happen so easily. You won't do it in a second or 2 or 3. It'll probably take maybe hours or days or probably, even months. X, if you are given a message, X, it's infeasible to find another message, Y, that they'll share the same hash. So if you have, that's what I said earlier, if you have this message and you have its hash, it's going to be very difficult to find another message that has the same hash. This is the strength, this is the main point in hashing. It's easy to hash, it's very difficult to reverse, very, very difficult to reverse. And that's why they're successful. And not all hash functions are good. Many people produce hash functions that aren't good. And hash functions can be evaluated, how difficult it is to reverse, and also how collisions, how many times do you get the same the same message? Because a different message will give you the same hash. It's going to happen, but we call that collision. It should resist birthday attacks. Birthday attacks are probabilities kind of theories or probabilities attacks is that you can just guess and guess within a certain range. So it should resist that. Birthday attack is based on an idea now. If we ask everybody here when is their birthday, the probability that there will be at least 2 people that have the same birthday within a group, because the birthdays is a number that's 300 out of 365. If you had any more than 365, definitely there'd be 2 people with the same birthday. If you had 365 people or more of them. But they say no, because it's so random that even if you get a smaller group, like a group of 50 people, there's a high probability that there'll be 2 similar people with the same birthday. When we do the experiment now, what do you want to shout their day and month of birthday? We don't need the year. When is your birthday? What month and what year? February what? 5th of February. What about you?
22nd August.
Okay. If you hear your birthday, then we stop the game. 15th of April. Tomorrow, is it? Hey, what's it today? Hold on, what day is it? Anybody has the same birthday? No. If you hear your birthday, come on. What? July 19th.
December 22nd.
Same. Same. There you are. This is called the birthday attack. Trying different probabilities within certain range. And if the range is small, then the hash, the hash of a message, you can actually just try, guess it, and send a message. It doesn't work, send another one. Maybe one of them is gonna, somehow. If if the hash function does not resist that. So the hash function has to resist that. Right, hash functions assumed to have no keys. That's the major difference between hash functions and MAC numbers. And the length should be large enough to resist the birthday attack. So the actual hash should be, the bigger the hash, the safer the hash function. So you know, and they started increasing those in the different standards that came out. They started increasing the hash function. It should be complicated enough. It should be complicated enough. That means it takes a bit of, you know, computation. It should have the diffusion function. It should have the diffusion property. What's the diffusion property again? You remember, no? No, I know. Okay, and do you know the diffusion property? Yeah, no? What's the diffusion property? No? Yeah, okay.
Hide the relation between plain text and ciphertext.
The diffusion is hiding the relation between the input to a function and the output. For example, if we got a message here and we encrypted it or we hashed it, it will produce an output, whatever it is, the hash function. If you take this, if you actually try it, test it, you give it a sentence or a message you know, and the hash. And then you give another one. Try and find a relationship between this and that, and then out of that you work out what the key is, or what, in this case there's no key, but how to break this hash message, or how to generate another message that gives the same hash. It should be difficult. That's what diffusion is. Brute force attack also requires a very long time. And still, even though it needs a bit of computation, that's complicated, but it needs to be extremely fast. And that's the major advantage. So it's quite secure and quite fast. But remember, what do we mean by secure here? The integrity of the message, not confidentiality. Remember, MAC and hash do not provide confidentiality. They're only used where integrity is required. If you need confidentiality, they're no good. They're not good. You might as well. And why do we use them and not use the encryption system? Not using the encryption system. Why don't we just use the encryption system? Forget about hash function. Any idea? Because the encryption system can actually provide us with confidentiality. It can provide us with integrity. If I want to send you a message that's integrity, I encrypt it. If you can decrypt it and make sense, then yeah, it was not changed. If anybody changes it, it's not going to decrypt successfully. So why don't we just use encryption systems instead of hashing? Any idea?
Because hash is smaller and unique in unique sense.
Well, hashing, well, also encryption will produce a unique kind of encrypted ciphered message of a function, of a message.
Because it's fast, sticking to the size of the hash function is always going to return a fixed size. So growing it.
But that's not a major advantage because you have to send the message. In fact, if I am to encrypt, I'll only send you the ciphered message. But now with hashing, you must use the actual message untouched, unchanged, and you send the digest. So you're actually sending more, even though it produces small, but what you end up sending is more than what the encryption. But the point, hashing is much, much faster. Like to encrypt a very, very large document takes a very long time. But to hash it, it takes very little time. It's a small digest and encrypt only that digest if you need to. So if we need integrity, we don't have to do any hashing. You don't need to do any encryption. You can do just integrity. If I want to send you a message that has no confidentiality, anybody can read. But when you receive it, you want to make sure it has not been modified. We can do it by encryption, we can do it by hashing. hashing is a lot faster, but you still have to send the message and the actual digest. But if we want to do digital signatures, a lot faster to reduce the message before you encrypt it. Encryption is necessary if you want to do digital signature or authentication. Authentication, all digital signature always needs the sender to encrypt the message with the sender's private key. That's the only way we are certain if they have, if that person who has one key that no one else in the world has and they use it to encrypt the message. That's the only way to authenticate a message. But instead of encrypting the entire message, now we can hash the message into a small piece very quickly, and then the user can encrypt that hash, the small part. So it's a very, very quick and fast way for doing digital signature and for authenticating messages using hashing. That's the only time that it has an advantage. But it doesn't provide confidentiality. You need to know, on its own, it does not provide confidentiality. On its own, it doesn't provide, digital signature. Digital signature still requires an encryption by the sender, by the sender's private key. That's the only way you're going to authenticate or digitally sign something. It's just with big messages, it's going to be very slow to encrypt the messages. So we reduce them to a small hash and we encrypt the hash. Okay, so birthday attack is just a way that you can have more probabilities of getting it by guessing if the size is small. That's why the larger the size, the more difficult it is to break. Let me keep going. Hash functions and max security, brute force attacks, exploiting the strong collision resistance hash level. So if the hash function has a strong resistance to collision, like usually they take a hash function, if somebody comes up with a hash function, they start testing it. And by testing it, they try and encrypt so many messages, hash so many messages, and see if they produce the same hash. If they produce similar hash or summary, that means that's collision. It's a weak one. And that's one way of, maybe comparing hash functions. If you are given two hash functions to compare which one is better, obviously the one that has less collisions. Max with known message, MAC pairs can either be attacked by key space or MAC, or at least 128 is needed for security. So you need at least size 128 or higher. Analysis attacks exploit some properties of algorithms so faster than exhaustive search. Hash functions use iterative structure. It rates the same function over the size of the message. We've already been through that. So it takes a block of a message, perform its operation. This is very much like CRC. If you're aware of networks, how networks work, or error detection system, very much similar. You go through the message a bit at a time until you finish the message. You always carry whatever is left, and when the message stops, when you finish with the message, then that last block is usually considered the hash. Hash functions, they've been developing over time, and right now, usually the actual hash is 512 bits, and the actual block size that they work on is 1024 bits. So over time, like with hash functions, secure hash functions, and then they kept developing different algorithms or different standards. Every few years, they increase the size to make it secure. So finally, this is just to describe how digital signature works. you're already aware now how to digitally sign a document. Anybody remembers how to digitally sign a document? Who was listening to me on this side? Come on, guys. Right, okay. How about you? You know? I know you were listening. You were with me. Go on. Tell me how to digitally sign a document, 3 or 4 or 5 steps, or just simple words. What do you start with if you want to digitally sign a document? Right, what's the first step? I have a document, I want to send it to somebody, and they say, sign it digitally. So what's the first thing you need to do? Here's the message. Anybody has any suggestions?
Summarize the message.
Yeah, that's hash it. Let's say hash the message. So there it is. We take the message, we hash it to produce a hash, which is a summary. Very good. Now what's the next thing? Anybody, what's the second?
Encrypt with the private key, sender's private key.
Encrypt the hash, not the message, the hash with the sender's private key. It's A, I'm assuming A is here, and R is for private key. So A is private key. If this is A, that's B. And then, what do we do after that? We got now a hash that's encrypted. What's the next step? What do you do next? That's it. You send the message and the signed or the encrypted hash. That's the signature. That's the digital signature. But that's only digital signature only, not for any other message. Why? Because we encrypted the summary of this message. That's the hash of this message. So every time you want to send another different message, you must sign it differently. It's not the same signature you append. So you get another message, you take the message, hash it, encrypt the hash using the sender's private key, and append it to the message. You don't mix it, you append it at the end. So the receiver can identify, here's the message up to there. The message is not encrypted in digital signature, unless if you want to encrypt it, that's apart from the digital signature. But what's the purpose of digital signature? Does it provide confidentiality? Why do we digitally sign a document? For what purpose? For confidentiality? Or integrity? Or authentication? It's authentication as well as integrity, but definitely not confidentiality. Digital signature does not give you confidential document, but it gives you an authentic document that you know who sent it, who signed it. And also, it has not been changed. If it's changed, if anybody changes this message, then what the receiver does, let's finish what the receiver does. The receiver receives a message and a digital signature. He doesn't know whether it's the same for this message or not. So he takes a digital signature, decrypt it. Decrypt it using which key? What key?
The key of the receiver.
The receiver's public key, right? Good answer. That's the wrong answer. Which key was used to encrypt the message? The private key of the sender. Yeah, then what key can be used to decrypt the message? Always, if a sender key was used to encrypt it, also then the other sender key that has to be decrypted. Okay, always remember this. The same person, or if we use if I took a message and encrypted it using the receiver's key, then the receiver must use its other key to decrypt the message. So both keys must be used to encrypt and decrypt, either both keys of the sender or both keys of the receiver. So now if we use the private key of the sender here, then we must use the public key of the sender. That's what this one, see A here and A, that's user A and user B. So both keys that belong to A are used to encrypt the message, to encrypt the digest of the message. And once, right, so we decrypted this, we got the original, this was encrypted, this digest was encrypted, we decrypted it, so we have now the plain digest unencrypted. The receiver has to hash the message as well. So remember, in hashing and macking, the sender hashes the message and also the receiver hashes the message. and the receiver compares the two hashes, the two summaries. And if they are the same, then that's where we say, okay, no change has happened. But also because we are able to decrypt this and it works. I mean, and we are able to decrypt it using the sender's public key. I mean, this was encrypted using the sender's private key. And that's hashing and macking and digital signature in few words. And there are definite exam questions. So make sure you understand. They're not complicated. If you understand it, it's simple to talk about it. If you don't understand it, make sure you understand it. Because it is an exam question. Well, every topic we take, the exam is going to have one question from every topic we covered. Like there'll be encryption or decryption of messages using all the decryption algorithms we had. And as well as the theoretical stuff here, that digital signatures and RSA and DES, and we still have to do PGP next week. And let me just remind you again as well, before I forget, but it's on Moodle, we will have a class test on the 25th of April. That's in 2 weeks from today. Class test in 2 weeks. I hope you weren't planning on going away on holiday or something.
All topics will be included.
Except PGP, which we will not. We'll cover it next week maybe, but we won't finish it next week, so the class test will not include PGP. Yeah, but it'll include everything else. Definitely all the decryption algorithms. So go over all the encryption, decryption algorithms that we've done, and everything basically, and key distributions. Right, okay, so this is really what digital signature is. So you can look at the diagram, it's a few different diagrams, but they all describe the same thing. So, any questions? Good. Now, how could we distribute our keys? If we had public key encryption system, everybody has a pair of keys. Name one technique, just name it, don't explain it. One technique that's used to distribute public keys. How do we spread them around? Of course, we can announce them. We can have a website that is a list of everybody, each member of us, and their public key. But we have to maintain it. We have to keep it secure because anybody can sneak in and change one of our keys. But any used, approved techniques that were used or are still in use. Using the public key authority. That's like one place that you have to go in and give them your public key and show them your ID, and they keep it and they maintain it. And if anybody wants to communicate with you, they need to ask for your public key, and it's given to them. Yeah. Any other technique for distributing public keys?
Certificates.
Public key certificates. Public key certificates is a certificate that has your ID and your key encrypted using this organization's private key. So it can be authenticated. We know who generated this certificate. And if you don't know, you can check it out. But that's the key, and they give you this certificate. It's a small, file that contains your name, your ID, and it's encrypted. And they probably give it to you in plain text format as well, just because it's not confidential. But the encryption is just for authentication. And how do we authenticate? How do you make sure a message you sent me, I'm certain it came from you? How do we do that? Any idea? Can you tell us? How could somebody send me a message that I know it actually came from them for 100%? So
Using their private. Using their public.
By using their public key, and I use their private key to decrypt it. Is that what you're saying? Are you fasting today or something? Not after all this. No, I wanted. You shouldn't listen to him. You are going right, and then somebody said he said something to you, and he said you changed your mind. Okay. Right. How could you send me a message that I know for certain came from you? Yeah, you need to know this. If you don't know this, you're really in trouble. I'm sorry. You need. If you don't know it, go and start looking at it, whatever it is. Read or something. This is so simple. How do you know if you send me a message? First, how do I know that it never changed? Or how do I know it actually came from you, not from someone else with your name signed at the end? So how do I know it came from you and from no one else?
I'll use my private key.
Use your private key, that key that no one else in the world has except you, use it. And how do I confirm that? How do I?
Use my public key.
By using your public key. If I can decrypt the message using your public key, then the message was encrypted with your private key that you are the only one who has. And that's my only assurance that it came from you. Make sure you know that basic, just that basic idea. That to send somebody a message authenticated that's for certain came from you, you have to sign it with something that no one else in the world has. That's your private key. The sender must sign a message or encrypt a message using their private key. That makes it authenticated, or possible to authenticate. Authenticatable. And how do we authenticate it? By using the sender's public key. If you use anybody's public key and it works, then that's the guy, whoever owns that public key, is the one who sent that message. You need to know that, and you need to know, okay, no, we're not interested on authentication. If I want to send you a message, I want to know it's just nobody else can read it except you. Now, I'm going to ask you again now. Right, you want to send, I want you to send me a message. Nobody can read it except I. That's confidential message. How would you encrypt it and how would I decrypt it?
Encrypt by your public key.
So if you encrypt a message using my public key, it'll need my private key to decrypt it, and no one else has my private key. Yeah, that's a confidential message. But I don't know who sent it. That's the only thing about it. Okay, what else did we talk about? Digital signatures, hashing. And what's a hash function? Give me one statement that describes.
One-way function.
It's a one-way function. Tell me something about hash functions. Any single statement that it generates a small fixed size, okay, of any message. It doesn't matter what the size of the message is, the output of that hash function is always small and fixed. Not too small. You know now, if it's too small, it's going to be a weak hash function. It has to be 512 bits, at least, or bigger. Anything else? Can you tell me about hash functions?
It's really fast.
It should be fast. Yeah. I'll come back to you. Yeah. Give me something else about hash functions.
Faster than encryption.
It's a lot faster than encryption. That's one of its major advantages.
It should have a complicated algorithm.
It should have reasonably complicated algorithm that you cannot work out another. Yeah. Give me one
It's
of
really
the.
hard to brute force it. To have the same hash.
It should be difficult or infeasible to generate.
Of the same hash.
To find another message that has the same hash. So if you have a message that you hash it and generates a hash, then you can't have, it's difficult to find another message that will generate the same hash. All right, and how about birthday attack? It should resist birthday attacks. I mean, randomly trying to pick few messages and hoping one of them is gonna, be the correct hash. And what is it used for? What are hash functions used for? Anybody want to tell me here? Used for confidentiality? What do you think? Integrity. I'll come back to you. What about the Mac function? What's Mac function used for? Sorry, yeah, but you got the answer? Hash function.
Hash function for punctuality and Mac function for integrity. Is it right?
50% of your answer is wrong, and the other 50 is.
No, that's right.
It's not used for authentication or confidentiality. It's not used for confidentiality. It's not there's no confidentiality in hash function. Confidentiality you only get with encryption. What else? What other topics did we, is time up?
Yes.
Okay, I'll see you Wednesday, guys. Good luck. Thank you very much.
Hey.